Hello everyone, welcome back to my Chem Corner. So in this video we are going to learn portions related to class 12 or second PUC chemistry. We're starting with the very first chapter from physical chemistry, which is solid state. So in this video we will be starting with the introduction, which is we're going to talk about the characteristic properties of solid. So since we're talking only about solid state, we're only going to restrict our entire explanation only to solids. So as we know in solids, when you look at the way the atoms are arranged in a solid, they are very much close to each other. So when they're close to each other, the main reason of this is because they have strong intermolecular force of attraction. Then when you have strong intermolecular forces of attraction, which means they are very close to each other, basically they have a very short intermolecular distance. Basically when you take two different atoms in the same solid, their space in between them or the intermolecular distance is very short. They have a fixed position for consistent particles. Now if you see how these atoms are placed in a solid, they have fixed position. They don't change their positions. Now when you look at how they are placed in the solids and what sort of motion they have only vibrational motion, because they basically cannot move. They have a very short intermolecular distance. The force of attraction between any two atoms in a solid is very strong. So because of that they cannot move. There is no other motion in the solid. They can only have vibration about their same position. Now because of all this, they have a definite mass, a definite size and a shape. And here solids are rigid, they are incompressible, which means when you try to take a solid and you try to compress them, it's not possible to compress a solid. It's only because of all these points. Their intermolecular force of attraction is very strong. So because of that they are incompressible and they also have a high density. So that was about a small introduction on solids. Now from here let's move on to classification of solids. So when we do practicals also, we have learned about this particular classification in grade 11 or in first PUC. Whenever we give you salt for salt analysis, your teachers would have told you, when you look at the salt, what do you see? Right? Or when you take a pinch of a salt, what do you see? You can feel some crystals in them, and sometimes they are like talcum powder, very smooth, very soft. So we're going to base them on those two natures itself. We have two types of solids. One is crystalline and the other one is amorphous. You would have come across these terms again in practicals. So if you have, say, crystals, when you take a pinch of the salt and you can feel crystals, such kind of solids are called as crystalline solids. Then the other type of solids, when you take a pinch of it, it may feel like talcum powder that you apply on face or like chalk powder. Such kind of solids come under amorphous solids. So let's look at the characteristic features of each of these type of solids. Now if you look at crystalline solids, they have an orderly arrangement of constituent particles. And that is why crystalline solids have a definite geometry. Whereas if you look at amorphous solids, they do not have an orderly arrangement, therefore they don't have a regular shape. That's why amorphous solids are more powdery, they don't have a consistent arrangement of particles, that's why they appear powdery and they're very soft. Then crystalline solids possess short range and long range order, whereas amorphous solids possess only short range order. Let me explain you what the short range or a long range order is. Now if you're looking at short range and long range order, I have taken arrangement of crystals here. So basically this is a crystal, and in this I have small spheres which are placed next to each other. Same thing over here. Now in this case, if you see, you have an orderly arrangement, which means I have a yellow sphere and then I have a green sphere and then I have a yellow. So basically I'm having alternate yellow green spheres. So here if you see, when these neighboring particles are joined, if I'm trying to join these four here, I'm going to get a geometrical pattern, right? And when I try to look at the entire crystal, I'm getting the same pattern repeated again. So if I try to join the next set of square, I'm still getting the same pattern. If I had a next one, I'm going to get the same. So when I keep joining, I'm going to get a regular pattern, a regular geometrical pattern over a long distance. So this type of a pattern where I can get a regular method or over a short distance or over a long distance, this type of an arrangement is seen only in a crystalline solid. Alright, so if I'm looking of the same type of an arrangement in amorphous solid, here if I look at the arrangement of these spheres, I have a yellow sphere, then I have a green sphere, I have a yellow sphere, and then I'm having yellow again. So if you see here, the pattern of arrangement is very irregular. It's a very random arrangement. Similarly, when I go down, when I have a yellow sphere, then the remaining all three are green spheres. So there's a very irregular arrangement of pattern, but over a short range, which means here I have a yellow sphere, I have a green sphere, yellow and a green. So when I try to join the centers of these spheres, I'm getting a regular pattern. But that's not continued throughout the entire crystal. So which means here this particular arrangement is seen only over a short range, and this type is seen only in amorphous solids. So basically in a crystalline solids you will see both short range and a long range order, whereas in amorphous solids you will only see short range order. So basically you're talking about the arrangement of particle over a regular pattern, either over a short range or a long range. That's what your short range order or a long range order in a crystalline or an amorphous solid mean. Now, the next point of difference between both are crystalline solids have a very sharp melting point. They have a very defined geometry. They have a very consistent arrangement of particle. So when a melting point is done, they will give a very sharp melting point, a single value for a melting point. Whereas if I'm looking at the amorphous solid, melting point is going to be over a range of temperature only because they have a short range order. They have a very consistent arrangement of particle only for a small range, and then there's a variation again. So what happens is when you try to do a melting point, it's going to give you over a range of temperatures. Then the next one is anisotropic. So crystalline solids are said to be anisotropic, which means, say I want to measure some physical quantity. For example, I want to measure a refractive index of a particular crystalline solid. Now when I try to measure them in different directions, it's going to give me a different value. That is what anisotropy means. Now when I look at amorphous solid, it is going to be isotropy. So say for example, in this case I want to try to measure a physical quantity, which is velocity of light. So when I look at amorphous solids, they're isotropy, which means the physical quantity that's measured in an amorphous solid will give me all identical value no matter in what direction I measure them. So basically crystalline solids are anisotropy, which means they will give different values in different directions. Isotropy for amorphous solids meaning they will give the same value in all directions. All these are only based on how the particles are arranged in that particular solid. Now the next one is, say I'm taking a crystalline solid and I want to cut it. Now because they have a consistent arrangement of particles, they have both short and long range order, no matter how I cut it, it's going to give me a smooth surface. But the same thing when I do it with an amorphous solid, it's going to give me a irregular surface because there is no orderly arrangement of particle at all. So when I cut it, it's going to give me an irregular pattern. Then we're going to talk about definite value for enthalpy of fusion. So what is the meaning of this enthalpy of fusion? Let's break the term. Enthalpy basically means energy. So here, how much of energy change is required when you're trying to heat a solid? So when you do all this process, it's going to give you a definite value for a crystalline solid. Again, you get a definite value for a crystalline solid because there is orderly arrangement of constituent particle. But the same thing when I see for amorphous solid, they don't have a definite value for enthalpy of fusion because there is no orderly arrangement. So enthalpy of fusion is nothing but heat of fusion. It means it is a change in its enthalpy that is caused due to heat. That is the meaning of enthalpy of fusion. Then the next difference is crystalline solids are true solids. They have proper pattern of arrangement of constituent particles over a long range, over a short range. They have a very sharp melting point. When you try to cut them, they have smooth surfaces, therefore they are true solids. But if you look at amorphous solids, they are pseudo solids. It's because of all these points where they show no correct orderly arrangement of the particles. They possess only short range and they melt over a range of temperature. So these are few classifications, two classifications solid and differences between crystalline and amorphous solid. Now this particular point is very important for exam point of view. They can ask for 3 marks. Give any 3 differences between crystalline and amorphous solids. So that's an important topic for exam point of view. Now that we've learned about the classification of solids, we will move into classification of crystalline solids. So we learned 2 classifications of solid, amorphous and crystalline. Now we are going to learn classification of crystalline solids. So here we have 4 types of classifications of crystalline solids depending on bonding. We have ionic solids, we have covalent or network solids, we have metallic solids, and we have molecular solids. So here when you look at ionic solid, you can just take a simple example of an ionic salt like sodium chloride, basically talking about its ionic bonding. Then talking about covalent bonding, you would have learnt in first PUC. Diamonds have covalent bonding, so you can take an example of that. Metallic solids, you can take any metal in which you can have a metallic bonding. Sodium, potassium, any metal can be considered. Molecular solids, we will go into detail later because we have certain classifications under molecular solids. So examples will be in detail for that. So we will go into that later. So here let's go into in detail for each of this, looking into its characteristic features and certain examples. So here, ionic solids. Now if you look at ionic solids, as the name says, the constituent particles are going to be ions. So here we have 2 types of ions. One is cation and the other one is anion. So if you look at this picture here given below, is basically a crystal lattice of sodium chloride. So you have one cube here and then another cube behind, and another cube here and another cube here. So basically we have 2 layers of cubes placed like this, giving you a crystal lattice of sodium chloride. Now what are these spheres here? The bigger green spheres that you see are chloride ion and the smaller spheres that you see are sodium ions. So these are constituent particles of an ionic solid, and how are they held? They are held by strong electrostatic force of attraction. Now here, because the bonding is really strong, they are hard, they are brittle, and they have high melting and boiling points. It's not really easy to get a melting or a boiling point at a low temperature for an ionic solid. You need to heat at a much higher temperature. Then, when these are present in solid state, basically like a salt, they don't conduct electricity because these ions are not free to move. But the same thing when you try to melt them or you try to dissolve them in water, these ions will become free. Sodium ions will be free, chloride ions will be free. Therefore, they will start conducting electricity. Now, classic examples of these are sodium chloride, zinc sulfide, magnesium oxide. These are some of the examples of ionic solids that you can give. Now, the next one is covalent or network solids. For this, the example that you will look at is diamond. We know that diamond has only carbon and the bonding between them is covalent bonding. They're very strong. So here the constituent particles are covalently bonded non-metallic atoms. If you look at diamond, diamond has only carbon. Carbon is a non-metallic atom. So here the bonding between them is covalent. Between what? Between non-metallic atoms which will extend in a 3-dimension. So because they are extended in 3-dimension, they will be also called as giant molecules. Covalent bonds are strongly held at lattice points. It's not really easy to break diamond. Why? Because they have very strong covalent bonds. Because of that, they are hard, they are brittle and have extremely high melting point, higher than ionic solids. Now, in this case, in case of your covalent solids or network solids, they don't have ions or they don't have free electrons. Because of all this, they don't conduct electricity, therefore they are called as insulators. Insulators don't conduct electricity. They don't have free electrons. They don't have free ions. So they are called as insulators. But out of all these, you have an exception called graphite, which we had learnt in first PUC or class 11 in detail. Example of this is diamond and quartz. Now the next one is metallic solids. Now metallic solids, you can just take any metal like sodium, potassium, lithium, any metal. So the constituent particle in a metal is basically a positively charged ion, a cation, and sea of free electrons held by metallic bonding. Metals have a tendency to lose electrons, so obviously those electrons are free. And these electrons are held by metallic bond. Now, since the strength of metallic bonds will vary, it depends on the property of each metal. The metallic bonding is also going to vary in strength. Now, based on the strength of the metallic bonding, their melting points are also going to vary. Now, we all know that metals have a very characteristic feature of being highly malleable and ductile, which means you can beat them to thin sheets or you can draw them to thin wires. Both properties are possible in solids. So they are highly malleable and ductile. Now in metals, because they have a tendency to lose electrons, there are presence of free electrons. Therefore, they have very high electrical and thermal conductivities, and that's why you have metal wiring in electrical equipments and all of that. It's because of these free electrons that will help in conduction of electricity and will also help in thermal conductivity. So classic example you can give of any metal, sodium, zinc, copper, any metal can be given. Now the next one or the last classification is molecular solids. Molecular solids are basically soft. They have a very low melting point. These will tend to exist in liquid. They are in the gas state at room temperature and pressure. And these are non-conductors of electricity. They don't conduct electricity at all. Now, based on the nature of their binding forces, molecular solids can be classified as 3 types: non-polar solids, polar solids, and hydrogen bonded molecular solids. So, there are 3 types of molecular solids that you can classify: non-polar, polar, and hydrogen bonded. So, examples under each of these category will be solid iodine. They are non-polar. Solid HCl, which is polar because you have two poles, a positive pole and a negative pole. Hydrogen bonded is ice, basically water. Right? When you try to freeze water, the water molecules are bonded to each other because of strong hydrogen bonding. So let's go in detail for each of these classifications. So first one, you have non-polar molecular solids. Now under this, the constituent particles are atoms or molecules which are held by weak London forces. That is for non-polar molecular solids. Example is solid iodine. If you are looking at polar molecular solids, you want to form a molecule which is polar. So basically here the constituent particles are molecules which are held by dipole-dipole interaction. Basically a positive pole and a negative pole. So example will be solid HCl. And the last one is hydrogen bonded. So of course here constituent particles are going to be molecule. Their forces that are holding them together is very strong hydrogen bonds. Example is going to be ice. So these are a few points which are talking about differences between non-polar, polar and hydrogen bonded molecular solids. So these are few classifications of solid and further classification of crystalline solids that we have learnt along with example. So I have a table here. Now in this table we are going to fill this up with whatever information we have learned right now to just sum up or to conclude the entire video. So let's see how to do that. So here in this table, let's fill in for the type of solid, the first one being ionic solids. Its constituent particles here are going to be cations and anions. The binding force here is electrostatic force of attraction. The physical nature here was hard and brittle. Electrical conductivity in this case, they were insulators in solid state and conducts electricity in molten state. Melting point here was very high. The example for this can be sodium chloride. Now the next one here is for type of solids. We have covalent solids. In this case, the constituent particles were non-metallic atoms. The binding force in this was covalent bonding. Physical nature here was hard and soft in case of graphite, which is an exception. The electrical conductivity here was, in case of compounds like diamonds, they were insulators, but when you had a graphite as an example, which is an exception, they were conductors. That's only because in graphite we have benzene ring where there's delocalization of electron. Because of delocalization of electron, they conduct electricity. Melting point here is very high because of covalent bonding. Example that you can give is diamond. Now the next one here is metallic solids. Under metallic solids you will have only cations or positively charged ions. The type of bonding is a metallic bonding. Physical nature here is that they are hard, malleable and ductile. Electrical conductivity, they will conduct electricity. Melting point here is fairly high. An example for this, you can give any metal. Now the next one is for molecular solids. Under molecular solids we learned non-polar molecular solid. Now the non-polar molecular solid, we have atoms as constituent particles. The binding force here was London forces. Physical nature for this, it was soft. Electrical conductivity, it was acting as an insulator. Melting point in this case is very low. An example for this is solid I2. Then we have the next classification, which is polar molecular solids. Under this, the constituent particle is a molecule. The binding force in this case is dipole interaction. The physical nature of this is soft. This will act as an insulator. The melting point here is low. And an example for this is HCl. And the last classification is hydrogen bonded molecular solid. In this case, the constituent particle is a molecule. The binding force in this case is hydrogen bonding. Here, physical nature of this is hard because the hydrogen bonding is very strong. Electrical conductivity, again, it's an insulator. Its melting point is low, and an example for this is ice. So here, the very first thing that we will look into is crystal lattice and unit cells, basically talking about the basic definitions of lattice points, about crystal lattice and unit cell. So first, before we move into the definition, we need to know what these terminologies are when you look at a diagram. So say I have a crystal here and I have cubes connected to each other. So basically I have 4 cubes on top interconnected and 4 cubes below. Both of these are connected to each other. Now each point in this cube is the atom or the sphere. So here, if you're considering an atom or a sphere which is trying to connect each of these points and trying to form a cube, is nothing but your lattice point. And each cube is called as a unit cell. So out of an entire crystal, one particular cube is what you call as a unit cell. And the individual spheres are called as lattice points. Now let's look at the definition of each of this. Lattice points are points that indicate relative points, positions of constituent particles in a crystal. So it's talking about the position of a particular particle in a crystal, and that's called as a lattice point. Now talking about a crystal lattice or a space lattice. Now the definition of this means it is a 3-dimensional arrangement of all these spheres. Basically talking about how these are arranged in a 3-dimensional position and trying to show a shape. That is nothing but your crystal lattice. And the last definition is the smallest repeating unit of a crystal, which when repeated in 3 dimensions gives a crystal lattice, that is called as a unit cell. So each of this cube, as it keeps repeating to form a crystal, that particular smallest unit is called as a unit cell. So these are the 3 different points that you will come across every now and then when we are going to learn any topic in this chapter. We will come across the term like lattice point, you will come across term like crystal lattice, you will come across a term like unit cell. So you should know what these terms actually mean. So lattice point is the point which indicates the position of the particle. Crystal lattice is when we have this lattice point in a 3-dimensional arrangement, then that's going to be called as a crystal lattice. And when each of these unit is going to repeat, creating an entire crystal, the repeating unit is called as a unit cell. So now let's move on to classification of unit cell. So here, when you look at a normal unit cell, which is basically a simple cube, such kind of a unit cell is called as a primitive unit cell. The constituent particles present at the corners of the unit cell or the corners of the cube is called as a primitive unit cell, or you can just call it as a simple cube. Now the next one is centered unit cell. So say if we are sitting in a room, you're sitting in a room right now listening to this video, the room itself is considered to be a cube, right? So you are sitting somewhere in the center of the cube, and this entire cube is the room. So at each corner of the room, I have spheres. So that's considered as a simple cube or a primitive unit cell. But what do you mean by centered unit cell? I can have another sphere right in the center of the room, hanging in the center of the room. Then that could be called as a body-centered unit cell. So here if I have, say, a unit cell here, a simple cube, and the center of the cube I'm having a sphere. Now that's called as a body-centered because it's the center of the unit cell. So it's called as body-centered. Now, what do you mean by face-centered? So look at the simple cube on the top. Each cube has 6 faces, 2 on top and below, and 4 on each sides. Right? So total 6 faces a cube has got. Now, the center of each face, if I have a sphere, that kind of a unit cell is called as face-centered unit cell. So here on this particular face, I have a sphere. So it's called as that one part has a face-centered sphere. Similarly, if I'm looking at this particular face here, at the center, I have a sphere. So these, like this, I will have at all 6 faces. I'm going to have one sphere in the center, and that's called as a face-centered unit cell. Now, the last type of a centered unit cell is end-centered. I'm going to consider any 2 ends of a cube, either top and below, front and back, or right and left. So if I consider any 2 ends of a cube, the center of those 2 ends will have a sphere. So here in this diagram, I'm considering top and bottom. So here if you see the top of that particular unit cell, in the center, there is a sphere. At the bottom, right in the center of that particular face, there is a sphere. So here, this is called as end-centered, which means at 2 ends of a cube, the center of the sphere has a sphere. Center of that face has a sphere. So this way we have 1 primitive unit cell and 3 centered unit cell, which is body-centered or BCC, face-centered or FCC, and end-centered unit cell. Next one, we will move into parameters of unit cell. So when I look at a particular cube with all spheres at each corners, I'm going to denote the edge length or the distance between the 2 spheres as A, B, C. So here I have, this is going to be named as A, this can be given as B, and this can be given as C. So basically, your edge lengths are being denoted as small alphabets. Now, each of these have bond length. Between A and B, I have a particular bond angle, and between A and C, I have another bond angle, and between B and C, I have another bond angle. Now, how am I going to denote these bond angles is just by putting alpha, beta, and gamma. So, in a unit cell, across, I think all textbooks when you take, it could be your reference textbook, it could be your NCRT, whichever. When you take these books, the edge lengths are denoted as A, B, C, and the bond angles are denoted as alpha, beta, gamma. Now that we know what these parameters are for, let's take the examples of 7 types of primitive cells and see what are the differences in the bond angle and what are the differences in their edge lengths. So let's see that way we're going to have 7 different primitive unit cells in crystal lattice. So let's see one by one. In this case, we're going to start with the simple cube. Now, when we look at a simple cube, its edge length and bond angles are all the same. So here we can write A is equal to B, which is equal to C, which means all the edge lengths are the same. Below that, I've written alpha is equal to beta, which is equal to gamma, which means to say that all the bond angles are equal. But what is the bond angle? the bond angle is equal to 90 degree. Next one is in a tetragonal. So for a tetragonal, if you see, A is equal to B, which means A here is equal to B. The bond angles are the same. But the one that's present perpendicular to A and B, which is the C, is not equal, because if you can clearly see the picture here, this length of C is longer. So A is equal to B but is not equal to C. But in this case, if you see, all their bond angles are equal. And if you take this bond angle, which is alpha, if you take this bond angle, which is beta, if you take this bond angle, which is gamma, all their bond angles are going to be equal. But what are they equal to? 90 degree. Now the next one is orthorhombic. Now in orthorhombic, if you see, edge length of A is smaller, B is slightly bigger, and C is even more bigger. So in this case, A is not equal to B, which is not equal to C. But if you see all their bond angles, they are all at 90 degrees. So all bond angles are same. Now the next one is rhombohedral. Now in rhombohedral, here the edge length of A, B and C all are of the same size. But if you look at the bond angles, though they are all same to each other, they are not equal to 90 degree. It is a different bond angle, but bond angle of alpha, beta and gamma, they have the same value, but they are not 90 degree. Now the next one is monoclinic. Now in monoclinic, here if you see, A is not equal to B, which is also not equal to C, because the bond angle of A, the edge length of A, the edge length of B and the edge length of C, they are all different. So here all their edge lengths are different, but the alpha and gamma is equal to 90 degree. But beta alone is not equal to 90 degree. If you can see, the entire diagram is a little tilted. This particular angle is beta and it is not equal to 90 degree. But the remaining two, gamma is here and alpha is here, that is equal to 90 degree. Then the next one is triclinic, in which nothing is same. Not a single edge length is same, or not even their bond angles are same. They are not even equal to 90 degree. So none of these are tallying with each other in a triclinic primitive unit cell. The last one is a hexagonal primitive unit cell. In this case, if you see, A is equal to B. These are equal to each other, but the C is slightly longer. So A is equal to B, but not equal to C. Now if you're looking at the bond angle, the alpha is equal to 90 degree. Beta is also equal to 90 degree, but gamma, if you see, it is 120 degree. If you see, the angle is slightly longer. It's a slightly bigger angle. So in this case, alpha and beta is equal to 90 degree, but gamma is not equal to 90. It is equal to 120 degrees. Now the next one is, we're going to find out that when you take a particular unit cell, how many atoms actually belong to that unit cell. So before that, I will just show you a particular crystal in which I'm going to talk about what you mean by this number of atoms in a unit cell. So here I've got one cube which is going on repeating to form an entire crystal. But if you look at, say for example, I'm taking this particular sphere. This particular sphere in the center, the one that is being marked on the screen, if I'm taking that particular one, if you see, that sphere is being shared among so many cubes, right? So this particular sphere is shared with this pink cube, the one behind the pink cube, the one below the pink cube, and the other side of the pink cube, and the opposite side cubes. So if you see, a sphere is not actually belonging completely to a unit cell. It is being shared among so many unit cells. So that way, when you're talking about how many spheres actually belong to one unit cell, we need to find out by a certain calculation. Alright, so this particular number is nothing but coordination number. Coordination number is defined as number of particles immediately adjacent to each particle in a crystal lattice. So this particular sphere is in coordination with this sphere, with the next sphere, with the one above and one below. So in this case, this particular center sphere is in contact with 4 other spheres, and here also this sphere and this sphere, 2 on the other sides. So totally the sphere over here is in having a coordination number of 6. So this way we are going to calculate number of atoms per unit cell in different types of unit cells. So let's start one by one. So we'll start with a very simple one, which is the primitive unit cell with a simple cube. So here I'm having the simple cube. Now I need to find out that when I have this simple cube bonded with other cubes, I need to know this particular sphere is actually belonging to when it belongs to one particular cube. What is its contribution? Right? So here number of atoms per unit cell is equal to 8 at the corner. So I'm taking one particular primitive unit cell. How many spheres are there or how many atoms are there? 8. But what is its contribution to others? If I'm taking the same sphere which is over here, the pink one, and if I'm considering this as to be one of the sphere for which I'm going to find out the contribution, it is going to this pink sphere. It is shared with the one behind. It is shared with the one below. It is shared with the one front of it. So this way 4 on one side and 4 behind it. So totally 8 unit cells this particular sphere is being shared with. So that's why I'm writing 1 by 8. That is the contribution. Now when I simplify this, actually for a primitive unit cell, only one atom belongs to itself. The others all are shared. Alright. Now the same thing when we look at the next one, which is the body-centered unit cell. So for a body-centered unit cell, this is the diagram where I have 8 spheres around in the unit cell and 1 sphere in the center. So for this, when I see the 8 spheres that are there around is still the same as the primitive unit cell. I have 8 at the corners, and when I consider this to be in an entire lattice, what will happen? Each of this will be divided among 8 other cubes. So 1 by 8 as contribution. When I try to solve this, I'll get 1 atom. What about this one in the center? If you see, I have one body-centered sphere and it is not actually being shared with any other cube. So it's just 1. So when I try to simplify this, I will get 1 atom here. And when I try to add up, I will have 2 atoms which is belonging to a BCC. This is not an addition sign. This is a multiplication sign here. Please just correct it when you all are looking into the video. It's a mistake. This is a multiplication sign. So here for a BCC, there are 2 atoms that are belonging to itself. Now when I look at number of atoms in a face-centered cubic unit cell, this is the structure for an FCC. Now when we try to repeat the same thing in the entire structure, the first part of the calculation is constant for all types of unit cell. 8 at the corners and 1 by 8 as contribution. Therefore, 1 atom will belong to itself. But since we have 6 spheres at the center of each face around the entire cube, we have 6 face centers. Now, out of that, so say this particular face is attached to the next cube here. So that sphere that is there in the center is being shared among 2 cubes. Therefore, I'm writing 1 sphere shared by 2 cubes here. So this at this particular face at the center, if I'm having a sphere, that particular sphere is shared with the pink cube and the one that is there next to it. That's why it's 1 by 2 as contribution. When I try to solve this, it will be 3 atoms. So total 4 atoms belongs to FCC, 1 unit cell of FCC. So this way we will calculate number of atoms per unit cell for a primitive cube, for a body-centered cube and for a face-centered cube. For a primitive cube, it's only one atom. For a body-centered cube, it is 2 atoms. And for a face-centered cube, it is 3 atoms. So that is with the entire video where we're talking about the basic definitions of a crystal lattice and a unit cell. We looked into the 7 types of primitive cells in a crystal, and then we saw that when we have these unit cells, how many atoms actually belong to a particular unit cell. About problems on how to find the formula of a compound. So in the last video, we learned about how to find the number of atoms that belong to a simple cube, to a BCC and FCC. So we are going to use that information to find out the formula of a compound. So let's see how to do that. We'll move into the very first problem. So the question 1 says, a cubic unit cell is made up of 3 elements. So we have 3 elements here, X, Y, and Z. Now of these 3 elements, atoms of X are present at the corner. So if you're taking a cube, or if you're sitting in a room, you can imagine that each corner of the room is occupied by atoms of X. Atoms of Y are at the cube center, just like your body centered. When you're sitting in the room, the center of the room has a atom which is denoted as Y, and atoms of Z at the center of each face. So the room that you're sitting in, each wall, the center of each wall is having a sphere or an atom which is atom of Z. So this way, X are present at the corners of the cube, Y is present at the cube center, and Z is present at the center of each face. Keeping these information, you need to find out what is the formula of the compound. So before we move into how to find the formula and all of that, we will have to compare this question to how to find the number of atoms per unit cell, which we did in the previous video. If you haven't watched that video, I'll put that link in the description box. Please do watch it before you solve problems based on this. So now, what have they given in the question? X is present at the corners, Y is present at the cube center, and Z is present at the face center. So we are going to solve it individually for each of these atoms. So the first one is number of X atom that's present per unit cell. It is only said that X is present at the corner, which means it is for number of atoms of a simple cube. So here we will take the calculation of a simple cube for X atom. So 8 are present at the corner, and out of that only 1 of it is being shared with 8 of the other cubes. That's why it's written as contribution. When we solve this, it will be 1 atom. This you get from number of atoms per unit cell for a simple primitive unit cell. Now let's look at Y. Y is present at cube center. Now when we talk about cube center, we're talking about a BCC or a body centered cube. So for this, at the cube center only 1 atom is there, and its contribution is only 1 because that particular atom is belonging only to that particular cube. When we solve this, you get only 1 atom here. Now the last one is Z, which is at the face center. So if you're having an atom which is present at face center, then those kind of a unit cell is called as face center unit cell. So we're going to take our calculation for Z from there. We have 6 face center into 1/2 contribution, which means 1 of the sphere is shared with the same face of the next sphere. That's why it's written as 1/2. This is also there in the previous video that I had taught you all. So kindly go through that, only then move into the problems related to this. So when we solve all of this, we have 1 atom, and 3 atoms. Therefore, the ratio here is going to be 1:1:3. So the formula of the compound here is XYZ3. So here, only if you know how to calculate number of atoms per unit cell for a simple cube, for a body-centered cube, and for a face-centered cube, it's easy for you to find out formula for a given compound from basic information given in the question. Now let's move into the second problem. The second problem is a cubic unit cell consists of 2 elements, P and Q. So in this case, we have only 2 elements. One is P and the other one is Q. Now, atoms of P are present at both present both at corners as well as face centers. So here P is present at the corner of the cube and it is present at each face center. So basically P has a face centered arrangement. And Q is present both on the edge center and the body center. So in the edge centers as well as body centers, basically BCC. What is the formula of the compound? So here what is given to us? The atom P is present at the corners and at the face centers, whereas Q is present at edge center, which means we have the edges of the cube, the center of that cube. Center of those edges it is present. So those are edge centers and body center. Now let's calculate for P. P is present at the corner. Now corners meaning it will be 8 corners and 1/8 contribution. Plus it is also present at the face center. So how many face centers do we have in a cube? 6 face centers. Out of that each atom is shared with 2 cubes. So that's 1/2 contribution. When we add up both you will get 4 atoms of now P. So here we have taken the first half is for simple cube, the second half is for face center. Let's try to do the same thing for atom Q also. Now for atom Q, the first thing what it says, it is present at the edge center. If we draw a cube and if you count how many edges are there in a cube, we have 12 edges. And when we place the cubes one above the other and beside them, each sphere on one cube is shared with 4 other cubes. So if you can imagine yourself sitting in a room, you have one room above yours, one room beside you, and one room, the one beside you, there's one above that. So what happens? There are 4, right? And when there are 4 like this, like just like this cube, you have one here, you have one here, and one in below this and one below that. So what happens is, say for example I want to check this particular line. I have a center sphere at the right in the center of it. Now what happens here is, if I check how many it is shared with this cube, it is shared with this cube, and it is shared with this cube, and it is shared here. So what is the contribution? It is 1/4 because one sphere is shared with 4 other cubes. That is for edge center. Now the next one is a simple one. It is for a body center. Obviously one sphere is present at the body center. Its contribution is nothing. It is only belonging to that particular unit cell. So here when we calculate all this, 12 into 1/4 will be 3. 1 into 1 will be 1. When we calculate, it is 4. So here the total ratio is 4:4. When we simplify it, we will get 1:1 as the ratio. Therefore, the formula of this compound is PQ. Just a simple one. So for these type of problems, all that you need is, say, either a diagram that you can draw like this, or you can just imagine yourself sitting in a room which is of a cubical shape. You have adjacent rooms and you have rooms above or below, and you're going to imagine the spheres either present at the corner, they're present at the face center, or they're present at the edges of the wall, or they're present at the body center. So it's just all about imagination that will help you solve these problems much easier than mugging up how to solve it. So either a diagram, or imagine yourself sitting in a room which is considered as a cube, and then you go ahead and solve the problem. Then let's solve 2 more questions of the same type. The next one is problem 3. Here a compound AB has an FCC structure. FCC meaning face centered. Now while atom A occupies the corners of the cube, only the corners A is occupying, B are at face center. What is the formula of the compound? Very simple one. We will take the calculation of A of a simple cube and calculation of a B only the face center. Then when you calculate this, you will get what the formula is. It's a very simple question. So let's see first what is given to us in the question. A is at the corners and B will be at the face center. Very simple one. Now, number of atoms per unit cell. Where are these A atoms present? Only at the corners. So you take the calculation of number of atoms per unit cell of a primitive unit cell. So here it will be 8 at the corners and 1 by 8 of contribution, which will be 1 atom. Next, when we see for number of atoms of B per unit cell, because B is present at face center, you take the face center calculation. We have 6 faces in the cube. Out of that, for each face, 1 atom is shared among 2 cubes. So here it's 1 by 2 contribution. When we calculate it, you will get 3 atoms. Now here it's a ratio of 1:3. Therefore, the formula of the compound is going to be AB3. Very simple one. Now let's move into the last one, which is a bit different here. Now in this case, in a cubic type of unit cell of a compound, A atoms are at 1/2 face. So they are only present at 1/2 of the face. While B atoms are present at the corner. B atom is easy. I'll help you solve what are the A atoms. Calculate the formula of the compound. So here, when we talk about the given things in the question, A atom are present at 1/2 face and B are present at the corners of the cube. So now, when you look at this, let's try to solve it step by step. When we talk about 1/2 faces, first let's see how many faces a cube has. So here, the number of faces are 6 in a cube. When we say 1/2 faces, half is the contribution, right? This is the general contribution of an FCC into 6 at the face center. So here when we talk about this, it is only 3 faces actually, because it's saying 1/2 of the face. The number of faces are 6 in a cube, of which only 1/2 of this faces are occupied by A. So half of this is nothing but 3. Now, number of atoms at these 3 faces will be 1 by 2 of contribution into only 3 faces, because it's not present at all face. It is only present at half of the faces. So 1 by 2 into 3. When we calculate this, you will get 3 by 2 atoms of A. Now the next one is atoms at corner is easy. It is for a simple cube. 8 at corners and 1 by 8 of contribution, that is equal to 1 atom. So in this case, the ratio is 3 by 2 is to 1. So we will expect the formula of the compound to be A 3 by 2 B1. But these kind of formulas don't exist. Now when we look at a formula, say for example looking for a magnesium salt, it will be MgCO3, MgSO4, calcium carbonate will be CaCO3 or CaSO4 or CaCl2. So what happens? There is a whole number in the formula. So same way we have to do here. When we simplify this, you add up the ratios. Right? When you simplify this, your formula is called, so you multiply the ratios. When you have this, this will be 3A3B2. That is the formula of the compound. So this way, you will be able to solve or find the formula of a compound, provided you know how to calculate number of atoms of unit cell for a primitive unit cell, for an FCC or for a BCC. Now apart from this, there's a lot more of diagrammatic imagination, or your own imagination of you sitting in a room which is considered to be a cube. The corners of the room will have a sphere. The faces of the walls will also have a sphere in the center for an FCC, and right in the center of the room you have a sphere that will be BCC. So this way, if you are able to at least imagine, then solving such questions will be easier. So closed pack structures. So we're looking at the type of the arrangements in different dimensions of these atoms. So let's see one by one. Now here, due to stronger intermolecular attractions in solids, the constituent particles are closely packed in 3 dimensions, in 3 different dimensions. So we all know the characteristic features of solids, that all these atoms are closely packed, their intermolecular attractions are very strong, they are not compressible and all of that. So because of all these features, they form a very close packed structures in 3 different dimensions. So here we will be learning in detail regarding these close packed structures in 1 dimension, 2 dimension and 3 dimension. So before we move into this entire video, I would like to say that when you are learning about close packed structures, all that you need is a lot of imagination regarding how these atoms are placed. If you're good at diagrams, then it would be nice if you could draw a diagram. But otherwise, a lot of imagination about how these atoms are going to be placed in a 2 and a 3 dimension. 1 dimension, yes, can be drawn on a paper. It's easier to identify, it's easier to understand. But when you move into 2 or 3 dimension, you're moving into other axes when you're looking at it. So there, a lot of imagination is required when you're trying to understand close packed structures in 2 and 3 dimensions. That's why I told imagination of how these atoms are going to be arranged would be helpful. Or if you want to know an easy way of learning 2 or 3 dimension, you can use bangles. Probably you have your mom's bangles or your sister's bangles, or any, you can use those bangles, try to arrange them on the floor or on a book, and then try to understand how the close packed structures on a 2 or 3 dimension works out. So let's move into each one in detail. We'll move into the close packing in 1 dimension. Now what do you mean by 1 dimension? It's just along, all the atoms are placed only on one particular axis. So here I have a diagram. Now here if you see, the atoms are placed in a row, just in a row, along one of the axes. So here if you see, the spheres are arranged in a row touching one another. They are in contact with one another. That's why we say solids are closely packed. Now each sphere is in contact with 2 of its neighbors. So here if you see, I'm taking the second atom. Which are these other atoms that it's in contact with? The first atom and the third atom. If I'm taking the third atom, it is in contact with the second and the fourth one. If I'm taking the fourth atom, it is in contact with the third and the fifth one. So in this case, if you see, each sphere is in contact with 2 of its neighboring atoms. So when we say that it is in contact with 2 other neighboring atoms, there is a particular terminology for it. It's called as coordination number. Coordination number meaning how many spheres are in contact with that particular sphere, or how many spheres are touching that particular sphere. So the coordination number of this particular atom is 2 because it's contacting 2 atoms. Thus, coordination number of this particular atom is also 2 because it is touching 2 atoms. So, in a 1 dimension close packing, the coordination number of any particle is going to be 2. So, here 1 dimension is easier because you just need to learn how these atoms are closely packed only in a single axis. Now, let's move into the next one, which is close packing in 2 dimension. So here now you need some imagination, right? When we were small or when we were kids, when we had when we had a lot of balls, what did we do with those? We tried to arrange them in a single row and then we tried to place them one above the other. That's exactly the same imagination that you're going to have even now. So here for 2 dimension, what are you going to do? To the existing 1 dimension, I am going to place rows above each other. So here I have 1 dimension. So this 1 dimension, what are the different ways in which I can actually arrange rows above this? There are different ways. Either I can place right above each sphere, or I can place in the depression of each of these spheres. So I have 2 different ways in which I can actually place my row number 2. So here for my clarification, I am going to name this first row as row number A. And now when I'm trying to place the second row, I'm going to place the second row exactly above the spheres of the first row. So here if you see both the rows are the same, So I'm going to name this also as A because both the rows arrangement are the same. Similarly, I'm going to keep arranging them the same way above. So what happens? I'm going to get the same arrangement in the third and the fourth layer and so on. So here each row in this type of an arrangement is A type because they're all placed in the same arrangement. They're all placed one above the other. So this type of an arrangement in a two-dimensional way is called as A type of arrangement. Now, say for example, can you all see a box here? Right? What was this box all about? I connected the centers of these four spheres. This particular sphere, center. This particular sphere, center. This sphere, the center. And this sphere, center. When I connected the centers of these spheres, what was the geometrical shape that I got? I got a square. Therefore, this type of a packing is called as square close packing. So the AAA type of arrangement is called as a square close packing because when the centers of these spheres were connected, they gave a geometrical shape of a square. Now, if you look at the coordination number of any sphere in this particular type of an arrangement. So in this, if I'm taking for example this particular sphere that is marked on the screen, this sphere, how many other spheres is it in contact with? This sphere is in contact with one above it, one on the right, one on the left, and one below. So totally how many atoms are that sphere in contact with? With 4 other neighboring atoms. So therefore, the coordination number of each sphere in this type of an arrangement is 4. Because any sphere that you take, it is touching 4 other spheres. So this is one type of an arrangement where you get a square close packing whose coordination number is 4. Now this is the type of arrangement where you get similar layers. Now I have another type of an arrangement. So I'm taking the same one dimension. Instead of placing my second layer one above the other of each of these spheres, I'm going to place them in the depression of these spheres. This is called the depression of a sphere. So I'm going to place it in the depression of the sphere like this. So now if you see, are the arrangement of layer 1 equal to layer 2? No, they are not the same. So what happens here? I'm going to name the second layer as B. The first layer is named as A. The second one is placed in the depression of the first layer, giving me an entirely different arrangement of the spheres. Therefore, that layer is named as B. Now what I'm going to do is when I place another layer on B, I'm going to place in the depression of the second layer itself. When I do that, I'm going to get this arrangement. Now when I compare the third layer with the first layer, their arrangements are the same. So that layer is going to be named as the same as first layer. Now on the third layer, when I place another layer in the depression of it, it's going to give me a layer similar to the second layer here. So here I'm going to name this as B because it is similar to the second layer. So here what type of an arrangement am I getting? I'm getting AB type arrangement. Now in this case, I'm going to connect the centers of the sphere. Right? When I'm going to connect the centers of the sphere, here I'm getting a hexagonal shape. I'm getting a hexagonal shape. So therefore, this type of an arrangement is called as hexagonal close packing. Now here, when you look at the center sphere, how many other atoms are the center sphere touching? 1, 2, 3, 4, 5 and 6. It is touching 6 other atoms, therefore the coordination number is 6. So for an AB type of arrangement, the type of close packing is hexagonal close packing, and each sphere is in contact with 6 other spheres. Therefore, the coordination number is 6. So here from a 1 dimension, when we come to 2 dimension, we have 2 different arrangement. One is when we place the second layer or the third layer right above the spheres of the first layer, then you get an AAA type arrangement whose packing is a square close packing and coordination number is 4. Whereas in the second type, when over the 1 dimension layer, when we place the second layer in the depression of the first layer, we get an AB type arrangement. In this case, the type of close packing is a hexagonal close packing whose coordination number of each sphere is 6. So now that we know what type of arrangements you get when you try to find the 2 dimension from a 1 dimension, we need to know what these gaps are. If you look at the type of a gap in a square close packing, it is different and much bigger when compared to the gap in a hexagonal close packing. So what is that space between the particle called as? The space between these particles are called as a void. Now this particular space is less in a hexagonal close packing. Therefore, close packing is more efficient in hexagonal type. What do you mean by more efficient? When we have a solid, when we say that these are closely packed and tightly packed, we need to say that the space between these atoms should be very less. That's when we say it is closely packed or tightly packed. So between the square close packing and the hexagonal close packing, which one has lesser space in between the particle? The hexagonal close packing. So that means close packing is more efficient in a hexagonal when compared to square close packing. Alright, so now we know how to find out the 2-dimensional close packing from a 1 dimension. Let's move into the next one, which is close packing in a 3 dimension. Now here we need a lot of imagination. Of course, I will be showing you the diagram, the model and all of that, but you need to have a lot of imagination so that you can understand how this entire concept of 3 dimension works. Now for a 3-dimension close packing, the 2-dimensional layers are placed one above the other. So say for example, I'm going to take my 2 dimension that I just learnt and I'm going to stack them one above the other. There are again 2 different ways. One is I can place one above the other, keeping the spheres right above the other. In the other one, what I can do, I can place in the depression, just like how we learnt a 2 dimension. Same way we are going to do here also. So here the first thing is conversion of a 2-dimensional square close packing into a 3-dimensional square close packing. So what do you mean by square close packing? The very first thing that we learnt under 2 dimension, AAA type of arrangement. So here let's take I've just taken a 2-dimensional square close packing and then I've just tilted the entire thing. So if I take, say, if I take an arrangement that's physically present in front of me and if I just kind of, slant it, this is the type of arrangement I will get, right? If I just push it from here and if I try to make it straight, it will be a proper square close packing. So I've just slanted it to show you all a 3-dimensional shape, so it's easy to understand. Now here, what I'm going to do is, I am going to place the second square close packing right above the first layer. So if you have not seen it, I will show it to you all once again. This is the first layer. When I place my second layer, I'm going to place right above the sphere of the first layer. You all can notice over here in the very first line. So if you see here, this is the second layer and that second layer sphere is standing right above the first layer. Now so on, when I keep doing it, what is happening in this case? In all the 3 layers that went above in the 3-dimensional shape, these are standing one above the other, but they are in a 3 dimension. So here the type of arrangement again in this case is AAA type, and this type of an arrangement will give a simple cube. This is the type of arrangement that you see in a simple cube. Alright, now if you connect the centers of each of these spheres, it is going to form a simple cube. That's why we say this type of an arrangement is seen in a simple cubic lattice, and the unit cell, one unit cell of this entire diagram is a primitive unit cell. Now let's move into the second type of arrangement, which is conversion of a two-dimensional hexagonal close packing into a three-dimensional. So now from the two-dimension we are taking the second type of arrangement, which is the AB-AB type. So let's see how to do that. So in this, the first thing is you're going to place a second layer over the first layer of a hexagonal close packing. Now hexagonal close packing from a two-dimension is the AB-AB type of arrangement, the second arrangement that we saw. Now when we take like that and we're going to place the layers one above the other, there are ways in which I can arrange them. So let's see the first type. So this is the AB-AB type of arrangement. That's a second dimension. Now if you see, I'm going to place the second layer in such a way it is covering the void. Some places the voids are covered, some places the voids are still visible. So that way when I cover it, I'm going to get different type of an arrangement. Now here, when I see this diagram like this, there are two different ways in which the atoms are placed. At some places you can see that the void of the first layer is covered with the sphere of the second layer. Now that is what is shown here. So this type of a void is called as a tetrahedral void. So when you try to connect the centers of the spheres, you will end up getting a tetrahedron. That's why the void there is called as a tetrahedral void or tetrahedral hole. But some places like here, these places, the void is clearly visible because there is no sphere covering it. Now, in such kind of places, it is called as an octahedral void, and when you join the centers of all the spheres in this type of an arrangement, you will get an octahedron. So that's why it is called as octahedral void. So now if you're looking at the total number of octahedral and tetrahedral void, if say in the entire close packing I have n spheres, we don't know the exact number, so we're just calling it as n spheres. So if n spheres are there in the close packing, then the total number of tetrahedral void will be 2n, double the number, and the number of octahedral void will be only n. So if you have n spheres, then number of octahedral void will be the same as the spheres count, but tetrahedral void will be 2 times the number. So this is regarding placing the two-dimensional hexagonal close packing one above the other in a way where it is closing the tetrahedral hole and the octahedral hole is still visible. Now what we are going to do is, in the second type of an arrangement, what we are going to do here is we are going to place a third layer. The problem is in the third layer. Are we going to place the third layer exactly in the type where the first layer is arranged, or we can have a totally new arrangement? So let's see that. So here when I place the third layer over the second layer, there are two possible arrangements. So this is the same arrangement we just saw in the previous slide, where some of the octahedral voids are visible, tetrahedral void here is covered. Now when I place the third layer above this, it can be same as the first layer, which is the yellow layer. That means I'm going to cover the tetrahedral void this way. So I'll go back and I'll show you what I did. I'm going to place the third layer. When I place the third layer, what is happening? The yellow spheres are not visible, which means they are placed right above the positions of the yellow sphere. So now when I try to tell the arrangement, the first layer and the third layer is the same. So here when I try to cover the tetrahedral void, AB-AB type of arrangement is observed, which means the arrangement of the A layer is equal to the third layer. So now the next type is where I'm going to cover the octahedral void. So let me take the same previous slide diagram. Now when I'm placing this, the void that was visible in the two layers, I'm going to place my third layer in such a way this void is now getting covered. In the AB type, that void was still visible. But here that octahedral void is going to be covered. So I place the spheres, the third layer in that way. Now when I placed it, what happened? I can still see the yellow layer. Nowhere the yellow layer is covered. So here I have covered the octahedral layer. In this case, I'm going to get ABC type of arrangement because the first layer, which is the yellow layer, is a different arrangement. The second layer, which is the gray layer, is also a different arrangement. On top of that, the red layer that I put is also a different arrangement because all three layers are visible to me. So it is ABC type of an arrangement. So when I cover tetrahedral void, it's going to be AB arrangement, which means repeated alternate layers are there. Whereas in octahedral void, when I try to cover, I'm going to get ABC type of arrangement. Now, in this type, when I'm trying to cover the tetrahedral void, the type of arrangement is AB type. Therefore, this type of an close packing is called as a hexagonal close packing because now in these three layers, when I place them in a three-dimension and try to connect all the centers of the sphere, I will get a hexagon. That's why they're called as hexagonal close packing. Now, in what type of metals are they formed? Metals like magnesium, zinc. These are the type of metals in which a hexagonal three-dimension close packing is seen. Whereas if I look at ABC type in this type of a close packing is called as a cubic close packing or a face-centered cubic close packing, FCC. Alright, so here this is found in metals like copper and silver. So here, for to understand this particular topic, which is talking about close pack structures in 1 dimension, 2 dimension and 3 dimension, a lot of imaginary diagrams are required for you to understand. So basically, if you can think of, say, if you have the same color ball with y'all, you can imagine how you're going to arrange them in a 1 dimension, then you're going to put them in a 2 dimension like one above the other, and then you're going to stack it up as a 3 dimension. But how many different ways can you stack them up? So that way it makes it easier for you to understand a closed pack structures. So let's move into this. Now packing efficiency, we're basically looking at the percentage of total space that is occupied by particles in a crystal, and that's called as packing efficiency. So we saw this the same thing in close pack structures when we looked at 1 dimension, 2 dimension and 3 dimension. We saw the efficiency of these particles being closely packed in it. Now we will look at the percentage in each type of a unit cell. Now that is a fraction of total space occupied by the particle is called as a packing fraction. Now we will be looking at packing efficiency in cubic close packing. We will look at body-centered cubic structures and in face-centered cubic structures. So we will be moving in detail. We will be calculating the percentage of packing efficiency in each of this. So the first one is packing efficiency in a CCP or a HCP. The full form of CCP is cubic close packing and HCP is hexagonal close packing. Now when you look at the structure here, naming of each of these lattice points and what these small a and small b are is important. So here the small a is nothing but the edge length and the small b is the hypotenuse. So we're going to use these terms and we're going to calculate the packing efficiency for CCP and HCP. So now we're going to look at basic mathematics. We're going to take triangle ABC. So we have triangle ABC. So this is the particular triangle that we're looking at. Now in that we're going to look at Pythagoras Theorem. So we have the square of the hypotenuse, which is equal to square of other two sides, sum of squares of other two sides. So here we have AC square, which is the hypotenuse, and which is equal to AB square plus BC square, which is the other two sides. Now here AC square is nothing but B square we can write, and AB square and BC square is nothing but A square. Those are the terms given. So we'll just write that here. Now A square plus A square can be written as 2A square after simplification. Because we need only the value of B, we will write root of 2A. So that is the value of B that we have got. Now, if the radius of the sphere is R, so we have these atoms here, these spheres. If the radius of these spheres are considered as R, in that case, we will have B is equal to 4R, because if you look at B, the line B, which is the hypotenuse, you have 3 spheres. Out of these 3 spheres, the first sphere, half circle is on this hypotenuse. So we have 1 radius over here. The center sphere has 2 radius, both of it are on the hypotenuse, and the last sphere, which is here, the half of the circle is on the hypotenuse. So totally we have 4R or 4 radius. So I've just written that 4R, which is further equal to root of 2A. Now when we further simplify that, A is equal to 4R by root 2. When you simplify this, you will get 2 root 2R. Now this is going to be the value of A. So let's keep that calculation aside. Now if you look at the unit cell of this CCP, these will have 4 spheres. Alright, so when it has 4 spheres, the volume of one sphere is going to be 4 by 3 pi r cube. Now this is the formula of a sphere, volume of a sphere. Now because in a closed CCP, each unit cell has got 4 spheres, therefore we are going to write volume of all 4 spheres is equal to 4 into 4 by 3 pi r cube. Simple calculation. Now because we're learning about a cube, volume of a cube is also prime importance. So here volume of cube is nothing but A cube. We just calculated what the value of A is, which is 2 root 2R cube. So we put that also. So now we know what is the volume of cube. We know what is the volume of all 4 spheres. We are going to write the formula of packing efficiency. So here in common, the packing efficiency is equal to volume occupied by the spheres in a unit cell divided by total volume of unit cell into 100. So this is going to be the common formula. What varies is depending on what type of a unit cell you're studying, whether it is 4 sphere, 1 sphere or 2 sphere, this is going to change. So here when we substitute the values, volume of 4 spheres is 4 into 4 by 3 pi r cube. We just wrote it here. Divided by total volume of the unit cell is here 2 root 2 r the whole cube into 100. When we simplify this, this is equal to 74%. So the percentage of packing efficiency in a CCP or a HCP is going to be 74%, the highest basically when comparing the other two. Now if asked whether you're supposed to calculate this using a calculator in your exam, not needed, because this is not going to change. It is going to remain standard. So you just have to write that 74% directly. You don't have to show calculation for this part here. But writing the formula, the substitution and final answer is important. Now let's move to the next one, which is packing efficiency in a BCC. Now when you look at packing efficiency in a BCC, you need to remember a BCC unit cell. So here if you see, this is across the unit cell. So this is like when you're sitting in a room and the center of the room you have a sphere hanging from the fan probably. So that is the sphere C in the center, right? So it is across the unit cell. Now here we are going to look at triangle EFD. So the calculation is almost similar to the previous one, but probably there would be an addition because you have an extra sphere placed probably in the center of the unit cell or probably in the face centers. So then you will have difference in the calculation of using the Pythagoras theorem, but the remaining part of the calculation almost remains the same. So here in this particular triangle, if you see EFD, the one that is at the bottom, that particular triangle, if you're seeing, you're going to apply again the Pythagoras theorem itself. So here if you see, your hypotenuse is this, FD. So FD square is equal to ED square plus EF square. EF square plus DE square. So here same thing, we have given the edges as A and the hypotenuse as B. That remains standard. So we'll just substitute the values. FD square is given as B here and the edge length is given as A. When we substitute it, it's going to be the same value that you get as you got in the CCP or HCP. B is equal to root 2A. Now that's not the only thing in a BCC, because we have a sphere right in the center of the unit cell. So we need to consider that particular triangle also. So let's see the second triangle, which is AFD, which involves the body centered atom also. So here when we look at AFD, in this case, the hypotenuse is AF. Now because it has the body centered sphere, we are naming that particular hypotenuse just to give a difference between this hypotenuse and the previous hypotenuse. That is named as C. So when we write down, we will write FA square is equal to AD square plus FD square. So FD is already named as B, which is the hypotenuse of the previous triangle. This AD is the normal edge length of any cube. AF is the new hypotenuse which contains the body centered atom. Now we'll just substitute the values into it. So FA is nothing but C, AD is A, and FD is going to be B. So when you put that, you will get an equation like this. Now every term here is different. You don't have further calculation, but there is one where you can make it simple. We had just calculated what is B, which is root of 2A. So instead of having A, we can just put, instead of having B, we can just substitute instead of B this entire value. So when we do that, we will get C square is equal to A square plus 2A square. When we put the value here, the root will get cancelled. You get 2A square. 2A square plus A square is equal to 3A square. So here, when we write C value, this will become root of 3A. So we have the value of B, we have the value of C also. Now, the remaining part of it remains the same, just like how we did for CCP and HCP. So here, if the radius of the sphere is given as R, in that case, again, on this particular hypotenuse, you have 4 radius. 1 radius from this sphere, 2 radius from the center sphere, and 1 radius from here. So total we have 4 radius. So therefore C is equal to 4R. On C we have 4 radius, which is equal to root of 3A. Now when we simplify that, you will get A is equal to 4R by root 3, because we need the value for edge length. So A is equal to 4R by root 3. Now we'll keep this aside. We will be using this directly into the calculation. Now we will see for a BCC how many atoms are belonging to it, which we did a calculation on in the previous videos. So here in each unit cell in a BCC has 2 spheres to itself. We did this calculation in the previous videos also. If you haven't watched that, I'll put the link in the description box and you all can watch how to calculate that. How many atoms belong to a particular unit cell. So here for a BCC, 2 spheres belong to itself. Now the volume of a sphere general formula is 4 by 3 pi r cube. So because each BCC has 2 spheres belonging to itself, so volume of those 2 spheres is equal to 2 into 4 by 3 pi r cube. Next is the volume of the cube. General formula is A cube. A cube is nothing but this, we just calculated here, 4R by root 3, the whole cube. So now we have the volume of the cube, we have the volume of 2 spheres. We can directly calculate the packing efficiency in BCC using the formula volume occupied by 2 spheres in a unit cell divided by total volume of unit cell into 100. So if you see the formula, the only difference between HCP packing efficiency formula and BCC packing efficiency formula is this value here. For HCP and CCP, which is generally observed in a face-centered cube, it was 4 spheres. In this case, because it's a BCC, it is 2 spheres. So now we'll just substitute the value. The volume occupied by two spheres we just calculated here, 2 into 4 by 3 pi r cube divided by total volume of unit cell, which is 4r root 3 the cube, which is, when we calculate this, you will get 68%. So here this is going to be the percentage for a BCC, 68%. Now let's move on to the last packing efficiency, which is a simple cube. This is much more easier because it's a very simplified version of whatever we learned right now, because we don't have a face-centered sphere, we don't have a body-centered sphere. This is just going to be a simple cube. So here I have a diagram for it. So we just have a simple cube. We're just looking at these two spheres which are there at the edge. There's nothing as such as a hypotenuse because we don't have any sphere in a simple cube which is coming on the face center or at the body center. So the calculation of the hypotenuse or the calculation using the Pythagoras theorem is not there in this case. So here we will see that in a simple cubic lattice, the particles are located at the corner. That's all. It's a very simple thing. So we will move directly into this. In this, the edge length is named as A, and it's named A throughout the entire packing efficiency that we learned. In this case, the radius is also named as R. So on one particular edge, if you see how many radius is there, from this sphere we have one radius, from this sphere we have one radius completing an entire edge length. So in this case, A is equal to 2R. We have only 2 radius. Now, when you calculated number of atoms per unit cell for a simple cube, we calculated there was only one sphere that actually belonged to itself. So here each unit cell in a simple cubic structure has only one sphere. Therefore, volume of that one sphere is going to be 1 into 4 by 3 pi r cube. Very simple one. Similarly, the volume of the cube A cube is equal to 2r the whole cube. We have the volume of the cube, we have the volume of the sphere. Write down the formula for packing efficiency, which is volume occupied by one sphere divided by total volume into 100. So volume occupied by one sphere is here and the total volume is here, 2r the whole cube into 100 substituted. When we calculate, you will get 52.4%. So if you see, the packing efficiency percentage is higher in a HCP or a CCP, which is found in a face-centered cube. And below that we have the BCC, and the least one is going to be for a simple cube. So here only three types are there. These packing efficiency is very important because in a PUC board exam paper, one packing efficiency problem for either 3 mark or 4 mark is there in the paper. It's a compulsory question. So please don't skip this part. Please watch. So here we are going to look at calculations involving unit cell dimensions. So basic things, we're just going to take out all the information from the previous videos that we learned, and we're going to find out the formula. So for this, we need the volume of the unit cell formula, which is nothing but A cube. Now the mass of the unit cell is going to involve how many atoms are there in that unit cell that's belonging to it. So if we're talking about a simple cube, only one atom belongs to the simple cube. And if you're looking at a body-centered cube, there are only 2 atoms that belonging to a body-centered cube. And if you're looking at a face-centered cube, there are 4 atoms belonging to it. And these numbers you get from a calculation that we did in the previous videos. If you haven't seen that, or if you haven't watched that video, I will put the link in the description box and you can just go through that video so you know what I'm talking about. Now, into mass of each atom. So that is the formula of mass of a unit cell. So here, mass of an atom present in a unit cell is equal to molar mass by Avogadro number. So here we have the formula. Small m, which is the mass of the atom, which is equal to capital M, which is generally given for molar mass, by Avogadro's number. Now from this, when we try to write on the formula of density, the general formula for density is mass by volume. So mass of the unit cell is given here, number of atoms in a unit cell, which is given as Z, into mass of each atom. Mass of each atom is given here, which is capital M by Na. So when we substitute the entire thing, mass of the unit cell is equal to Z, which is the number of atoms per unit cell, into molar mass divided by Avogadro number into volume of the unit cell, and the denominator is going to be A cube. So this is going to be the final formula that we are going to use to calculate the density when we have other values given to us. Now, before we move into the problems, whenever we do problems related to this, the values of these edge length will either be in two parameters. One is in nanometer, second one is in picometer. But we never calculate them directly. We never use these conversions directly. Instead, we need to show some conversion to centimeter or meter. So I'll show you what those conversions are. So when we have 1 nanometer, when we convert it to meter, it's going to be 10 to the power minus 9. Further, when you convert it to centimeter, which is normally the unit that you use in the calculation of a density, it's going to be 10 to the power minus 7 centimeter. So this is going to be the conversion when you move from nanometer to centimeter or nanometer to meter. Now another unit that can be mentioned in the problem is picometer. Now picometer, 1 picometer is equal to 10 to the power minus 12 meters, or it is equal to 10 to the power minus 10 centimeter. So these are the two units that are generally mentioned in a problem on density of this type. So you are all expected to know these conversions, because in the end, what answer you get has to be in terms of gram per centimeter cube for a density. So your conversion here is very important. So kindly use these conversions, kindly learn these conversions when you're going to solve problems related to density. So now let's move into the problem. So here the first problem is silver forms an FCC lattice, and X-ray study of its crystal show that edge length of its unit cell is 408.6 picometer. Calculate the density of silver whose atomic mass is 107.9. So here, these are the few informations given to us in the question. Let's put that down in the problem, in the solution, so that we are not confused when we try to substitute it. So let's write what is given to us in the question. First thing is A is given to us. A is nothing but edge length. Edge length is given to us as 408.6 picometer. Now I told that we will not use this picometer directly in the problem. Instead, we need to show its conversion. So we will convert it to centimeter. So 408.6 picometer, when you convert it to centimeter, is going to be 408.6, 10 to the power minus 10 centimeter. I've just shown meter here, so you know what the conversion looks like, but centimeter alone is more than enough. So now in this, when we write down this value in terms of centimeter, this is the value you're going to use in the substitution and further calculation. Now next one, what is given to us in the question is atomic mass of silver, 107.9 U. Now the next value that is not given but should be understood is in the first sentence here. Silver forms FCC lattice. Now the minute you know that this particular crystal is of an FCC lattice, the number of atoms per unit cell for an FCC is 4. Therefore, Z is equal to 4. So we know what is A, we know what is M, we know what is Z. And Na, which is the Avogadro's number, is a constant value, 6.022, 10 to the power 23. That should be known by heart. So we have all the values. Now we just need to substitute it in the formula and calculate the density. So we have Z value, we have M value, we have A value, which has to be cubed, and we have Na, which is a constant. Now the next one is we will just substitute it directly. Now when we substitute, Z is equal to 4 into molar mass divided by, we need to cube this entire A value along with the power into the Avogadro's number. So first what you will do in the calculation is you need to cube this and then do your further calculation. Now when you solve this completely, your answer here is going to be 10.55 gram per centimeter cube. So this is going to be your value for this particular problem. Now the next question is problem number 2. An element forms a BCC crystal. The unit cell edge length is 260 picometer. Calculate the density when the molar mass of the element is 23 gram per mole. Similar type of a question, but instead of having it as FCC, we have a BCC crystal here. So let's see what is given to us in the question. Similar type of values. In this case, Z is equal to 2 because it's a BCC. Number of atoms per unit cell for a BCC or a body-centered cube is 2. Now, A value is given to us in terms of picometer. When we convert it to centimeter, it's going to be the same power, 260 into 10 to the power minus 10 centimeter. Molar mass is also given to us 23 gram per mole. Avogadro's number is a constant. You are expected to know it by heart. It's a direct substitution to the formula. Now, density is equal to, just substitute all the values that you have here. Instead of Z, we have 2. Instead of M, we have 23. Divided by, instead of A, we have 216 to 10 to the power minus 10, the whole cube, into Avogadro's number. Cube it. You have to calculate the entire part and you will get your answer as 4.364346 gram per centimeter cube. Now, during the calculation, the entire calculation, one place where every student can go, can get a mistake is sometimes some students forget to cube this. Please don't do that, because when you forget to cube it, your entire answer is wrong here. So please remember that A cube should always be done in the calculation of density, only then move forward. So first thing when you substitute is calculate the cubed value and then you can move forward in this. Alright. Now let's move into the last question, which is problem number 3. Calcium crystallizes in an FCC lattice with an edge length 0.556 nanometer. So here the unit is different. Calculate the density of the crystal. So in this case, what is given to us is A value, which is in terms of nanometer. So the conversion that I gave you, use that conversion. So here, since it's nanometer, when you convert it to centimeter, it's going to be 10 to the power minus 7 centimeter. So that's why I told you, whenever you look at density problems in terms of packing efficiency, there are only 2 units that are mentioned to us. One is picometer and the other one is nanometer. Know their conversions to centimeter and you're good to go on the calculation. Alright, now where we have molar mass is 40 is not given to us because it's clearly mentioned that the element is calcium. You are expected to know the atomic mass at least. So calcium molar mass is 40. Then Z value is 4 because here it clearly says FCC. Number of atoms per unit cell for FCC is 4. Avogadro's number is a constant. It is by hearted. So you just substitute all these values in the formula. So instead of Z we have 4. Instead of M we have 40. Divided by A cube is 0.556 10 to the power minus 7 cube. So minus 7 is for conversion from nanometer to centimeter. Cube it into its Avogadro's number. When we calculate this entire thing, your value here is going to be 1.545 gram per centimeter cube. So here we have simple substitutions to your formula where you need to calculate density. The only thing to be kept in mind is conversion from picometer to centimeter or nanometer to centimeter. That's very important. And you should know the Avogadro's number by heart. Apart from that, everything else will be mentioned in the question. Read the question properly, clearly, and then put down the given value. Only then move forward in the calculation. So let's move into the topic, which is imperfections in solid. So here, when we've learned about crystalline solids and amorphous solids, these imperfections, as the name says, are observed in a crystalline solids. So here, crystalline solids, we've learned that they have a short range as well as a long range order. But in general, these crystals don't have a perfect structure. They're not in perfect geometry. But why does this happen? There are 2 reasons to it. These will happen either due to the presence of impurities or in case there is a dislocation of any constituent particle from their position. So these are the main 2 reasons why there are some imperfections in solid, or crystals don't have a perfect geometry, or even if they have a perfect geometry that could be disturbed is due to this. Now, when does this happen? When does this all impurities are there, or when does this dislocation of impurities, dislocation of constituent particles taking place? These are possible when we do crystallization. Each type of a crystal, when you try to do crystallization, they take their own time to settle. But when we do crystallization on a faster pace or on a moderate rate, what happens is these imperfections in solids are seen. Say, for example, when we try to suddenly cool something, you might find a hollow in the center, you might find some air space in center. This happens even if you're doing a normal cooking in the kitchen. When we say, for example, you're trying to bake, or all of these, what happens is if you don't do it properly, you might find some hollows in between, you might find some air spaces in between. It's the same thing in case of crystallization when you look at solids too. So when it's done on a faster pace or on a moderate rate, what happens is you might find these imperfections in crystals. So what is the definition of an imperfection in crystal or a crystal defect? Any deviation or departure from perfectly ordered arrangement of a constituent particle in a crystal is called as a crystal defect or an imperfection. Crystals are supposed to have its respective geometry, its respective arrangement of constituent particles. If there is a deviation from all that, if the shape is changing, if the geometry is changing, if the arrangement of these particles are changing, then they are classified under crystal defect or an imperfection in solid. So depending on the type of an imperfection, there are different classifications under it, whether they leave the crystal lattice or are they going and sitting somewhere in between, they will be classified differently. So let's look at the classification. So here we have different types of crystal defects. One is called as point defect and the other one is called as a line defect. Now what are these called as? What do they mean? What is a point defect? What is a line defect? Just go by the terms. In this case, point defect, you're talking about a particular point or a particular atom in a crystal. It is showing irregularities or deviation from an ideal arrangement around a point or around an atom in a crystal. That is called as a point defect. And the same way, if you're talking about a line defect, you are talking about an entire row of lattice points. So if there is a change in, or if there's a disturbance in the arrangement over an entire row of a lattice points, then they are classified as line defects. So if you go by the term itself, you get what the meaning of these defects are. Now what are we going to concentrate on? What are we going to go in detail and learn? We are only going to focus on point defect. We're not looking at line defect. We're going in detail with respect to point defect. So here point defects are broadly classified into three types. The first one is stoichiometric defect, second one impurity defect, and the third one is non-stoichiometric defect. Let's go by the term itself. Now stoichiometric meaning you are not disturbing the stoichiometry of that particular crystal. The stoichiometry remains undisturbed, or the ratio of number of particles remain undisturbed. These are also called as intrinsic or thermodynamic defects. They have other terms also. Now what about an impurity defect? Impurity defect is when you have an impurity. Another, say in an NaCl crystal, you're going to have a strontium metal. That's called an impurity defect because you're having an entirely different cation in that particular crystal. So that is broadly classified as impurity defect. What about non-stoichiometric defect? Now non-stoichiometric defect is going to talk about those defects where the ratio is going to be disturbed. It's right opposite to a stoichiometric defect. Now under stoichiometric defect, we have four types of defects. We will go in detail for each one of them separately. We have vacancy defect, we have interstitial defect, we have Schottky and Frankel defect. We have four different types of defect for which we will go in detail in upcoming slides. Now, as I told you, non-stoichiometric defect, the stoichiometry is disturbed in this case. Alright, so maybe you have another metal going to be replacing a particular metal, then the entire stoichiometry is going to be different because sometimes you might have an incoming metal with a different valency. In that case, probably you might have an introduction of an electron there, or you might have a vacancy there. So it's all going to be disturbed completely. That is going to be classified as non-stoichiometric. There is no stoichiometry. That's what it means. Now, non-stoichiometric defect can be classified as two: metal excess defect and metal deficiency defect. So, like I told you, if you have another metal coming in picture in that particular crystal, you can have a metal of a different valency. In that case, you're going to have a metal excess defect, because in that particular crystal, you're going to have more number of metals right now. If you're talking about metal deficiency defect, you could have a removal of a metal probably, but you might have say an introduction of an electron in that case. So what happens there is that you're having deficiency of a metal, right? So these are the two types of non-stoichiometric defects. One is metal excess defect, the other one is metal deficiency defect. Now, under metal excess defect, we have two different types. One is caused by anionic vacancy and the other one is caused by excess cations. So each of these we're going to go in detail, and we're going to learn what are the properties of it, how does it happen, and which type of examples are these type of defects generally seen. So we will go in detail in this video. Now the next one that we're going to talk in detail is about stoichiometric defects. So let's learn about that. Now under stoichiometric defect, we learned four types. We learned about vacancy defect, we learned about interstitial defect, we learned about Schottky defect, and we learned about Frankel defect. Now under vacancy defect, just as the name says, you have a perfect crystal here. Alright, there are all atoms, or there are all these lattice points here. But what is happening? In this case, one of the atom is moving out. So what's happening there? There is a vacancy here. There is an empty space here. So that means the point or that particular atom is missing. So when some of the lattice sites are vacant, the crystal is said to have a vacancy defect. So there are chances where these happens, right? When you do sudden crystallization, maybe one lattice site could go missing. It could go out of the crystal. In that case, it will produce a vacancy defect. Now, because this is happening, it's moving out of the crystal, the mass of that particular crystal is going to reduce. It's just like we have a class of students and there's one student who's pushed out of the classroom. So what is happening there? The number of students in the class is going to reduce. The strength of the class is going to reduce. Same thing here. When there is a lattice site that is vacant, which means that particular point or an atom is missing, the mass is going to reduce. When the mass reduces, the density of the crystal is also going to reduce. Now, when is it mostly seen? When heating of the crystal is done. When you start heating them, these metals can, or these points can go missing. Alright, so it's just a basic thing where when you heat, there is a lattice point that's missing, it moves out of the crystal and a vacancy is produced there. Now when this happens, the mass is going to reduce and the density of the crystal is also decreasing. So that's the first type of a stoichiometric defect. Now let's move into the next type of a stoichiometric defect, which is the interstitial defect. So here, as the name says, you have a perfect crystal here, same thing. But what are you observing here? Probably somewhere you have a cation which is of a smaller size. It could occupy the interstitial site. So say for example, whenever we make students sit in class, there are spaces in between two rows of students or between each student. So what happens if there is a small child in the class? The child can fit in those small spaces. The same thing here. The cations are there. Cations are generally smaller in size. So what happens is when you try to heat the crystal again, what will happen is these smaller cations can fit into these smaller spaces in the crystal. These smaller spaces in the crystal are called as interstitial site. So the particle is going to occupy the interstitial site. So in this case, what is happening? Because there is a cation that is introduced into the crystal lattice, the mass is going to increase. When the mass increases, the density of the crystal is also going to increase. So vacancy defect and interstitial defect are quite opposite. In the vacancy defect, a lattice point moves out of the lattice. But in interstitial defect, a cation can come and sit in smaller spaces in between these lattice points. So they are quite quite opposite to each other. Now, these vacancy defect and interstitial defect, where are these generally seen? These are generally seen in those type of solids which are non-ionic. So they're seen in non-ionic solids. But what type of defects are generally seen in an ionic solid? The remaining two types of defect, which is Schottky or Frankel defect. So the vacancy and interstitial defects are observed in non-ionic, whereas Schottky and Frankel are observed in ionic solids. So now let's move into the next type of stoichiometric defect, which is the Schottky defect. Now in Schottky, I have a perfect crystal here. So if you see these orange dots, they are all cations, and these gray dots are all anions. So when you see the next picture over here, what do you see missing? From this point, you see that a gray dot is missing, or an anion is missing. And over here, you see that a cation is missing, which is the orange dot. So here we can conclude that a cation and an anion both are missing from the lattice so that they maintain electrical neutrality. Now this is a condition observed in a Schottky defect. So you have a cation and an anion both missing from the lattice points, which will result in electrical neutrality. Now when this happens, because the cation and anion both are missing from the lattice points, the mass of this is going to reduce. And when the mass reduces, the density should also reduce. Now in which type of ionic solids are these observed? When the cation and anion are of comparable sizes, those type of ionic solids, the Schottky defect is observed. So I've given you a few examples. You can choose any one of it when you're writing an example. You have sodium chloride, potassium bromide, cesium chloride, and silver bromide. These are observed in these ionic solids. Alright, now the next one is Frankel defect, which is the last one under stoichiometric defect. So here when you see, you have a perfect crystal, but in the next diagram, what do you see? There is a vacancy here. What is missing? The orange dot is missing. Where has it gone? It has gone to some interstitial site here. So what is happening in this case? The anions, when the cations this arises when the cations will occupy interstitial site instead of moving to completely outside the crystal. So here what happens is you are finding a dislocation defect, because here the cation is getting dislocated from its normal site and it's moving to some interstitial site. So you observe an interstitial defect here. But in this case, you can also observe a vacancy defect because there's a vacant site here. So in Frankel defect, you can find both. You can find a vacancy defect. You can also find an interstitial defect. But what about Schottky? You can only find a vacancy defect. Now in this case, when you compare and see, is this particular cation that was here moving out of the crystal? No. It is in the same crystal itself. So what happens? No ions are missing. They are only getting reshuffled, right? It's just moving to an interstitial site. So in this case, the density remains unaffected. Okay, the density is unaffected in this case. Now, in what type of ions are they observed? In those ions whose cation and anion have a large difference. They need that difference, only then the cation can sit in the interstitial site. If they are of comparable sizes, what will happen? The size of the cation and the anion will be similar. So the cation cannot really sit in the interstitial site. So in this case, you should have cation and anion which differ in a large difference. Example here is zinc sulfide, AgCl, AgBr and AgI. These cations and anions have a huge difference between them. Now if you observe these examples, silver bromide is one of those examples that were there in both Frankel and Schottky. That means to say that they observe both of it. Why is that so? It is only because the radius ratio is an intermediate. They are not too small. The difference between them is not too large also. They are intermediate. So what happens is they can show both defect. They can show vacancy and they can show an interstitial defect. Both Schottky and Frankel is observed in case of AGPR. That is one of the questions that they can ask for a mark in the exam. Why is AGPR observing both defects? It's only because the radius ratio between AG and BR is intermediate. They're not too small, they're not too big differences. So this is about the Schottky defect. Now when you learn about the Schottky defect, one common question that can be asked in the exam is differences between Frankel and Schottky defect. So what are you going to do? Just write the summary of this in a table. And that's exactly what I've put down here, the differences between Schottky and Frankel defect. So under Schottky and Frankel defect, the very first one that can be written here is, you can write the definition between them. Schottky arises due to missing of cations and anions and hence maintaining electrical neutrality. Frankel defect you can write when the cations occupy the interstitial site than the normal site. When you look at a Schottky defect, you can say that they observe a vacancy defect, whereas Frankel defect has interstitial defect. Now in Schottky defect, because both cations and anions are missing, the density is going to reduce. But in Frankel defect, because it's only moving to an interstitial site, the density is going to remain unaffected. Now under Schottky defect, these are generally observed by cations and anions of comparable sizes, whereas in Frankel defect, they need large differences between cation and anion. So these are a few differences between Schottky and Frankel defect when asked in the exam. Never give examples as a point of difference. They are not a point of difference. You're not trying to tell any difference between them when you are giving an example. Examples are only given when asked in a question, not in a difference. Alright, so that was all about Schottky defect. We will now move on to the second type of a point defect, which is called as impurity defect. So as the name says, it is due to an impurity. Alright, so here let's see how that happens. So here I have a crystal. In this, if you see, it is basically an NaCl lattice. But what is the impurity in this? Strontium. If you see here, Sr2 plus is the impurity. How does this happen? When does it happen? All this is what we're going to learn under this. So here, you're going to consider crystallization of a molten NaCl in the presence of small amount of SrCl2. When you do crystallization in the presence of it, what will happen in this case? Some of the Na plus ions can be replaced by Sr2 plus because it's happening in the presence of SrCl2. Some of the ions here is going to get replaced with strontium ions. Now what happens is when you try to replace them, if you observe their valencies are different. Na is with a +1, Sr is with a +2. So to maintain that electron count or the electrical neutrality, what will happen is because Sr is with 2+, you need to replace 2 sodium ions. 2 sodium ions should be lost to accommodate 1 strontium ion. Now when you do that, what will happen? There is a cationic vacancy that is observed. Right? One of the sodium ions is occupied by Sr2+, but the other place is going to be vacant, and that is going to be a cationic vacancy. So in this case, what is happening? The number of cationic vacancy produced is equal to the number of strontium ions that is introduced. If you have introduced only one Sr2+ ion into the crystal lattice, you will have only one vacancy. If you have introduced two strontium ions, then you will have 2 vacancies. So this is only due to an impurity in the crystal lattice. So that is all about impurity defect. Now the next one is the third type of a point defect, which is a non-stoichiometric defect. Under that, the first one is a metal excess defect. So as the name says, it is due to an excess of a metal in the crystal lattice. So here, let's see how to do this. The first one under metal excess defect is going to be bianionic vacancy. A metal can be excess if an anion can move out of the crystal. Okay. So here again we're taking a classic example of sodium chloride. When sodium chloride crystals are heated in a sodium atmosphere, what will happen? Sodium ions are going to accumulate on the surface of this crystal. Now, when sodium ions are going to get accumulated, what will happen? Some of the chloride ions are going to move to the surface. So when that happens, the accumulated sodium atom will lose an electron. So whatever sodium atom is there at the surface, it will try to release an electron and it will form sodium plus ion. Now when that happens, whatever Cl minus comes out of the crystal, it is going to form NaCl with that sodium atom. Now what happens to the electron that's released by the sodium? It is going to take place. It is going to be sitting in the place where that anion came out. So it's going to be entrapped in the anionic vacancy. Therefore, the crystal will have excess of sodium. Alright, because one Cl atom has moved out, now it will have excess of sodium atoms in there. Now the anionic vacancy that's containing this electron has a particular name, and that's called as F center, or it's called as Farben center. Now what is the responsibility of that electron? What is the point in that electron being there? When we do salt analysis in practical in first year, what did we observe? When we do any salt analysis procedure, we always do a flame test in the group 5. Now in that, when we do, we always see a flame test in the confirmatory test. How is that coming? It is because of this particular electron. When the salt is heated, the electron is going to undergo excitation, absorbing some visible region. Now what happens? Because of that, it's going to result in a flame color. That is why sodium when heated will give you golden flame, golden yellow. Potassium gives you a lilac color. When you heat your calcium, it gives brick red. Strontium gives crimson red. Barium gives apple green. It's because of that particular electron undergoing excitation. So this is all about metal excess defect due to anionic vacancy. Now the next one is the same one, metal excess defect by the presence of an extra cation in the interstitial site. So here when we look at zinc oxide, when you look at it room temperature, what is the color? It's white, right? But when you heat it, what will happen? It is going to lose an oxygen atom. So here I take zinc oxide, and when I heat it, it's going to have zinc 2 plus with the release of electron, and oxygen is formed. Now what will happen? There is excess of zinc 2 plus in the lattice. The excess of zinc 2 plus, where is it going to go? It will move into the interstitial site, because zinc is a metal, a cation. It's a smaller size. So it's going to move into the interstitial sites and electrons to the neighboring interstitial sites. Now when this happens, there is excess of zinc in the crystal. And those electrons which move to the neighboring sites is undergoing excitation, and therefore zinc will now give yellow color when it is hot. So in this equation, this zinc is going to occupy the interstitial site. The electron that is here is again going to give you color of this to the flame when you try to heat. That is why zinc oxide at room temperature is white, but when it is heated, it gives you a flame color yellow. It's because of this entire process. Alright, and now we have the last type, which is metal deficiency defect under non-stoichiometric defect. So here if you see, this defect is observed in metals exhibiting variable valency. So in your periodic table, if you think about those metals which exhibit variable valency, where are they observed? They are observed in the D block elements, right? Where you have your transition metals. So in this case, if you're looking at an example, you're taking a crystal FeO, iron oxide. So in this case, in iron oxide, some of the Fe2 plus is missing from the lattice, and their positions are occupied by required number of Fe3 plus ions to maintain electrical neutrality. So when Fe3 plus ions, which has higher valency, is occupying Fe2 plus ions, what is happening? Naturally, there is a lesser number of cations. So in this case, you will observe that the less amount of metal is present, which is needed to maintain stoichiometric proportion, right? So there you have metal deficiency defect observed. So here some of the sites of Fe2 plus are occupied by Fe3 plus, which is of a higher valency. So generally when this happens, you will have lesser number of ions, or you have metal deficiency defect observed. So these are a few defects that you see when you look at a crystal and when you study them in detail. Depending on what type of a crystal that you take, you will find these many defects in it. So in this video, we're going to talk about the electrical properties, which are basically conductor, insulator, and semiconductor. So we all know that conductor is something that conducts electricity, and insulator is something which has a low conductivity, which means it doesn't conduct electricity at all. A classic example of a conductor is any metal, right? So if you have any metal, copper or a zinc, any of these would conduct electricity. An insulator like a diamond, which is a classic example that you've learned in first year, that is going to be an insulator. And there's something else called a semiconductor, which has an intermediate conductivity, which means it cannot conduct electricity by itself, but it requires a support of another element in order to show conductivity. So in this chapter, what are we going to focus on? We're going to focus on semiconductor in detail. But before we move in detail about semiconductor, how the semiconductor is going to conduct electricity and all of that, we will be just brushing through basic things about conductor. So when we talk about conductor conducting electricity, how does it actually happens? Because of what does it actually happens? Or if you're talking about an insulator that doesn't conduct electricity, what is the reason? Why is that so? What are the things that are responsible that insulator do not conduct an electricity? So that's what we're going to just brush up through it. So let's move into that. So here when we're looking at conduction of electricity, we're going to talk about conduction of electricity in a metal, right? So here the conductor conducts electricity through movement of electron or ions. We all know classic characteristic feature of metal is it can give away electrons. Those electrons are the ones that are responsible for conduction of electricity. Now, how much is going to be the conductivity from each metal? It only depends on number of valence electrons that are available. So if you take each metal, the conductivity value is going to be different for different metals, only because it depends on how many electrons are there in the last orbital of every metal. Atomic orbitals of metal atoms form molecular orbitals which are so close in energy so as to form a band. So here, when you're talking about a band, this is what a diagram of a band looks like. So when you're talking about conductors over here, the valence band is nothing but the outer shell electrons that are arranged in the metal. That is basically what the valence band is. Now what happens here is when the electrons are excited, say for example you're trying to heat that particular metal, what is happening? The metal is going to absorb the entire heat, and who's going to be affected with this? The electrons that are present in the valence orbital. So the electrons that are there in the valence band is going to jump to the conduction band, which is the higher excited state. Now when this electron jumps from the lower excited state, which is the lower state, which is the valence band, to the higher excited state, which is the conduction band, there is a conduction of electricity. So here the energies are so close that electrons can easily jump to the conduction band. Now if this band is partially filled or it overlaps with the higher energy unoccupied conduction band, then electrons can flow easily. So here, if the conduction band is very close to the valence band, which means you don't have to apply much energy for the electrons to jump, in that case, you will have conduction easily. Or if you have a partially filled orbital also, these electrons can jump easily, and it can show conductivity also. But if the gap is too large, just like how you see for insulators, the gap between the conduction and the valence band is more. In this case, there is no way the electrons can jump. So here you will see behavior of an insulator, which means they will not conduct electricity. Alright, so that was all about conduction of electricity, just brushing through the the basic concepts that you know about conductors and insulators. Now moving on to the main part under electrical properties that we're going to focus on this year is conduction of electricity in a semiconductor. So here we all know, we've just seen the diagram also, that the valence band and the conduction band in a semiconductor is quite small. It's not as small as a conductor, it's not as large as an insulator, right? It's intermediate between both. They're smaller, which means they may jump to the conduction band. How? With increase in temperature. So the gap between the valence band and the conduction band is small in semiconductors, but electrons can jump only when you try to increase the temperature. So that is what we're going to learn under this semiconductor. So when you compare the band gap between each of this, if you see the gap in semiconductor is intermediate between both insulator and conductor. Now, what kind of elements in your periodic table do show these semiconductor character? These are substances like silicon or germanium, basically your group 14 elements. They show properties like a semiconductor. The conductivity of the intrinsic semiconductor is too low for a practical use. So say you want to do some experiment related in the lab, all of those. We don't generally prefer a semiconductor because the conductivity is much lower. So instead they prefer a conductor. Now, how are you going to increase the conductivity? We always say probably by increasing a temperature you can increase the conductivity of a semiconductor. But there is also a method where when you add small amount of an impurity, you can still increase conductivity. Right? By heating, yes, we can increase conductivity. But by adding a small amount of impurity, you can increase conductivity even more. So the process by which you're adding an impurity to a semiconductor so that conductivity increases is called as doping. Alright, so the process here is called as doping. Now, doping, how is it going to be done? You're going to use two types of impurity. One is an electron-rich impurity and the other one is electron-deficient impurity. So, for example, I am having group 14 elements, which is a semiconductor. My electron-rich impurity is going to be group 15 because it has one electron extra. Whereas if I'm talking about electron deficient, then I'm talking about group 13 element because it has one electron lesser. So this way, I'm going to use both group 15 and group 13 to do doping process so that group 14, which acts as a semiconductor, can conduct electricity. Alright, so this was just the introduction to a semiconductor. Now what we are going to do is we are going to learn how a group 13 element is going to help in doping, or how a group 15 element is going to help in doping, and what are they called as. Alright, so here we are going to use electron-rich impurity, which means I am going to use carbon family, which is the group 14 acting as a semiconductor. My impurity that I'm going to add is from nitrogen family, which is group 15. So in this case, when you're talking about group 14, which is a semiconductor, how many valence electrons do they have? They are going to have 4 valence electron, right? So when we are going to dope it with an electron-rich impurity, we are going to dope it with a group 15 element, basically nitrogen family, which is going to use phosphorus or arsenic. Now, if you say they are pentavalent impurity, what do you call by pentavalent impurity? Which means they contain 5 electrons in the valence orbital. So here, when you see these two, the group 14 is having 4 valence electron, whereas group 15 is having 5 valence electron. So in this case, 4 out of 5 electrons in the group 15 is going to be involved in bonding with group 14 elements. So out of 5 electrons that are there in group 15, only 4 are getting bonded to group 14. Now, what happens to the 5th electron that is there in group 15? The 5th electron is going to become delocalized because it is a free electron now. It is going to move around. Now, when it moves around, it is going to conduct electricity in the electron-rich impurity type of a semiconductor. So here, therefore, you're going to increase conductivity, and this increase in conductivity is only due to that negatively charged electron or that 5th electron that is present in this. So here, because you have that extra electron, this type of an semiconductor where silicon or germanium is doped with group 15 element is called as N-type semiconductor. Why is it called an N-type semiconductor? Because the one that is responsible for delocalization or for conductivity in this case is an electron. Electrons are negatively charged. So here N-type meaning negative type semiconductor, because it's an electron that's responsible for conduction of electricity, which we call this as a negative type of a semiconductor. So this is with respect to an electron rich impurity. But what happens when you have an electron deficit impurity or electron poor impurity? So here, when you're talking about an electron deficit impurity, I'm going to compare group 14, which is a carbon family, with group 13, which is a boron family. So here again, group 14 will have 4 electrons in the valence orbital, whereas group 13, which is added as a dopant, is going to be containing only 3 electrons. So in this case, out of the 4 electrons, only 3 electrons will be involved in bonding. What will happen to the 4th one? The place where the 4th electron is supposed to be present in the dopant is vacant because it has only 3 electrons. So here it is going to create an electron hole or an electron vacancy. Now the neighboring electron can try to fill that particular hole, and that positive charge is the one that is going to be responsible for conduction of electricity in the electron deficit semiconductor. So here what is happening, because you have a vacant orbital in the group 13 element, the neighboring electron can keep shifting in that particular hole. So what is the reason why there is conduction of electricity? It is because of an electron hole. It is because of an electron vacancy. What is the charge of the vacancy? Vacancy meaning it is always lesser, which means positively charged. Therefore, when you have silicon doped with an electron deficit impurity, we call it as a p-type semiconductor or a positive type semiconductor. So there in electron rich, you're going to add group 14 with group 15. In electron deficit, it's going to be group 14 with group 13. So that's the 2 types of semiconductor that are responsible for conduction of electricity only in the presence of a doping. So now that we know what happens in a semiconductor, let's see what the possible applications are. So here it is diode, which is a combination of both N and P-type semiconductor, is used as a rectifier. Transistors are sandwich semiconductors where one layer of one type of semiconductor is sandwiched between 2 other types of semiconductor. This you would have probably learned in physics. How is it going to detect radio signals and all of that? You use this type of a transistor. And last one, which is solar cells, is an efficient photodiode which is used to convert light energy into electrical energy. So these are some of the simple applications that you can have under N and P type semiconductors. So in magnetic properties, all that we're going to learn is different types of magnetic properties, their few characteristic features and examples under them. So first thing we're going to learn is about paramagnetic and diamagnetic, which is not a new magnetic property to anyone because we've learned the same thing last year with examples under molecular orbital theory from chemical bonding chapter. So the same points apply here. So under paramagnetic and diamagnetic, we basically learn a comparison because that's make our learning easier. So here under paramagnetic, these are weakly attracted by magnetic field, whereas diamagnetic are weakly repelled by the magnetic field. Paramagnetic, every electron is magnetized in the same direction, whereas diamagnetic, electrons are magnetized in the opposite direction. Now, under presence of what kind of electrons do these magnetic properties take place? For paramagnetic, it's due to the presence of unpaired electrons, and diamagnetic, it is due to the presence of a paired electron. Examples, you can either give these as examples or you can give from MOT from last year's syllabus. And the next one is a ferromagnetic substance. In this case, if you see, these substances are strongly attracted by the magnetic field and they are permanently magnetized. Right? So in solid state, metal ions are grouped in small regions called domains. Each domain will act as a tiny magnet because they have all electrons grouped together in small regions. But in their unmagnetized state, the domains are randomly oriented and their magnetic moments gets cancelled. In the magnetic field, these domains are oriented in direction of the magnetic field and hence they behave as a very strong magnet. And a classic example that you can give is iron or cobalt, one of these metals. But what about antiferromagnetic? So when you look at antiferromagnetic substances, these are substances which are expected to have high paramagnetic behavior, but they possess zero magnetic moment. Generally in paramagnetic substances, we don't have a zero magnetic moment, but in this case we have zero magnetic moment. They contain equal number of domains oriented in opposite direction. So you have all these electrons placed in opposite direction, therefore their magnetic moments will cancel out. Example is MnO. The last type of magnet is a ferrimagnetic substance. They possess unequal number of domains oriented in opposite direction. So when you're learning antiferromagnetic and ferromagnetic, they're right opposite to each other. In this, they have equal number of domains oriented in opposite direction. These, they have unequal number of domains oriented in opposite direction. Hence, because they have unequal number of domains, they have some sort of a magnetic moment. And because of that, they are weakly attracted by the magnetic field when compared to a ferromagnetic substance. Example over here is an ore of iron, which is magnetite. So this is just talking about the general basic characteristic of each magnetic substances and their example. So you just have to know these things and not any more in detail. So with this, we come to the end of the chapter solid state. If you have any queries, please don't hesitate to write an email to me, but you can always put down your suggestions in the description, in the comment box below, and I will be answering those queries. So stay tuned and have a nice day. Thank you.